identical, but areas are different? Is it possible to have identical areas, but different perimeters?
Yes.
How do we know?
Because our assignment showed it.
Because our assignment did that, right? Also, would you just pinch those two ends together so that it makes a circle? I don't want to tie it. Watch this. Can everybody see that rectangle? Now, if she keeps that pinched, the perimeter will maintain the same. Okay, so if I go like that, that one should have the same perimeter, right? But does it have the same area? Well, it's hard to tell because it gets skinnier, the width gets less, but the length gets longer, right? But I think it's obvious that this one and this one do not have the same area. Do you follow what I'm saying? I mean, I've almost collapsed it. And if I got it a little bit, my fingers weren't so fat, I could get it to go even thinner, right? And that area is definitely less than that area. Is everybody following what I'm saying? So it's pretty obvious that if I maintain a given perimeter, I can get it to be various areas. Okay? Thank you. This is something that students sometimes come to our classes with misconceptions about. Oh, you have the same amount of fence? Well, it will certainly enclose the same amount of pasture. And that's not true. We've got data from this bumper cars thing that shows that's not true. One day in class, I handed every one of my students, these were 8th graders, a blank sheet of paper, 8.5 by 11 sheet of paper, and I said, I want you to build me a rectangular box, a rectangular prism without a top. All you have is this, a pair of scissors, and some tape to put it together. And what I want you to do is build the biggest box possible. Now, the only thing that you could use the tape for was to tape your, like I could cut this and then fold it up, and then tape the flaps together. You couldn't build like rails around the top of your box with tape. That was, it was just to hold the box together. Well, students got busy cutting and taping, and I walked by one student and he was just sitting there and he goes, I said, how come you're not working on your box? He says, this is stupid. I said, what's stupid? He said, everybody knows if it's the same size piece of paper, the boxes will all hold the same amount. Well, I thought, no, that's not true. But what does a teacher do in a situation like that? You say, that isn't true, now get going on your box, or what do you do? Huh? Well, let me tell you what happened. I just thought, well, that's his belief. If he really believes that right now, me telling him it's not true isn't going to change his belief. Has anyone seen that video called, it slipped my mind. It was taped back at Harvard and MIT right at graduation. And they surveyed, what's the name of it?
No, I don't know.
Yes, the misconception about the earth and the seasons. And those people had been taught over and over again in junior high and in high school and in college again, and they still wouldn't let go of what they really believed, unless what happens? They have to, someone else can't tell them. Well, guess what happened the very next day? We took the students' boxes, filled them full of puffed rice, poured them into a container where we could measure the volume out, and it was obvious that they were all different volumes. And he still went along with what, well, they'll all make the same, and he's watching these, but he didn't get involved with it. He didn't get involved mentally, and he didn't get involved at all. just kind of watched. I thought, what am I going to do with this kid? But because if that didn't work, him seeing us pour the boxes full of rice and getting different volumes doesn't work. Telling him's not going to work. Do you believe me?
Yep.
Here's how it happened. Later on, we'd started with the 3-dimensional, and we went to 2-dimensional, and we did a problem kind of like your bumper cars one. And he was given so much fence and told to make pastures of whatever shape he... And it finally hit him, well, the same amount of fence can make different areas of pasture. And all of a sudden he went back, oh, so... And then he went... transfer that idea to the surface area and the box volume. But I want you to think about that. Sometimes we think as teachers, all we got to do is tell them, right? And they'll know it. But not always true. It's bugging me, the name of that. It'll pop into my head. Here we go. I'll be thinking about it. What I'd like you to do is pull out your hand size thing, and let's find out who thinks they have the biggest hand here. And let's talk about some methods that you used to determine your hand size. That's probably more important than...
I googled the name. It's a private universe.
A private universe, thank you. A private universe, because we all live in our own universe that's private, and nobody can change it until we change it ourselves. It's true constructivism.
Pretty impressive.
Yeah, thank you. Who thinks they got the biggest hand? No? Yeah. How big did you get?
I said 155 centimeters.
155 centimeters. Anybody get more than that? Okay. Who would like to see what happens when you don't come? Who could share with us how they went about that? Yeah.
Well, I traced my hand, and then I went back in, and I put an X inside every box within my hand, from there my hand shape. I put an X in every box that had a significant amount covered. So if only like a sliver to the next box, I didn't put an X.
So if they were whole ones or just had a sliver missing, you put an X? Is that what you're saying?
Yes, or if a significant amount was covered by my hands, I put an X in there, and then I just counted all the X's.
Okay. Yes.
I looked at the boxes, and I paired up boxes by, like, say if one was 50% covered and the other one was 50%, that made one whole box, and I counted that as a whole. Or if one looked like 2/3 was covered and the other one had 1/3, I matched that up, and that's a whole.
Ah, so you took parts and made up holes and added those in. Anybody else want to? Yeah.
I just did length times width.
Really?
Yeah.
You have a rectangular hand?
No, but like the sections that are like half and half are gonna make up for the ones that are not full. That's what I thought in my mind.
So do you have your thing there?
I do.
Do you want to hold it up and show us kind of where your length and width was?
So
And
I took like the highest point to the lowest point, and then from here to the thumb. So like these half boxes make up with the other half boxes. That's what I feel like.
which half boxes?
Like right here. That's not a whole box.
Okay.
That just is a sliver of a boxes. I mean, that's
Okay.
just what I thought.
Okay.
in my mind.
The only problem I would see with that is you have your hand spread out, and I can make the area of my hand a lot bigger if I'm counting width, because my height isn't changing, but I just like double the width.
That's true.
Unless you what?
Unless you count for the
Subtract out those ones in between your fingers.
You could do that.
Okay, so you could take, say, rectangle minus the parts that didn't, okay? Did somebody else? Yeah.
I did it just like that too, except I only did my palm area and then the area of each finger. Like approximately there was 12 to 15,
That's what I
about
did.
2 wide in each.
palm plus finger plus finger plus finger, so you did the area of each piece, kind of, and then put them together, huh?
So I actually found that by sticking my hand all close together, if I was to chop off the essentially first knuckle and a half of my middle finger and the first knuckle on my ring and pointer finger, and either set them down diagonally or up on my thumb, it's pretty much my pinky down and then over, and that's my hand. And so I
He's
decided-
back.
I think it's really important that you give your students at any age, high school or elementary, opportunities to measure areas of objects that are not common shapes like squares and rectangles and trapezoids, and you really should probably give them opportunities to do areas using non-standard units, like have everybody go outside and pick a leaf off of a bush or a tree and come in and say, how many leaves would it take to cover your textbook? So you're not measuring in square inches or square centimeters or whatever, you're measuring in leaves. And what are they going to do? Well, they'll probably lay it on their book and then they'll slide it over a little bit to where, and count each one, or, and why is that important?
Oh, I was just thinking because it helps you understand the concept instead of just the formulas.
Yeah, the concept of what does area mean? It might mean how many quarters would cover my book, or how many leaves would cover it, or
Well, especially with children with young minds, associating like a mathematic problem to a real life situation is going to help them more instead of these new words that they don't really fully understand.
what's a square inch?
Yeah,
Yeah,
I know what a leaf is.
but I know what a quarter is.
Mm-hmm. Yeah.
Okay? And you could do the same thing with area. You could say, well, what's the perimeter of your book in paperclip lengths? So they could lay it and then lay it and go all the way around their book. And then they get the idea of what perimeter is because they're not focusing on units as much as they are the idea of what it is. Okay. In class, last Tuesday, we came up with the area of formula for a rectangle, length times width. We used that to go into the area of a parallelogram. We converted that back into the rectangle and got base times height, where the base is one of the sides and the height is the perpendicular to that base. In the homework, I ask you to take and cut out a triangle. I would like to have someone share the method that they use to take the triangle either back to the parallelogram or back to Mama, the rectangle, all the way. Did anybody get it back to either of those? I'd like to share.
I made a parallelogram, traced the triangle again and put it one on top of the other.
Okay. So you duplicated your triangle. So here we have your triangle right here. Like this. You made another one. Put it right up here. Same as that one. Now we have a parallelogram. And so if this was length A, B, and C, how would we find the area of that parallelogram?
You do B times C.
B times C, will that do it? You're shaking your head.
C isn't the height.
So,
So we don't have a measurement up here that we need? Is that what you're saying?
yeah.
Where is the height? It's actually outside the altitude of this triangle is the distance from the base of the triangle or an extended base through the opposite vertex at a perpendicular, right? All right, so we would take, if that's h, we would take what? How would we find the area of this particular parallelogram?
Base times height.
Base times height. Base times height. So, area of a triangle is base times height, then? Since base times height gives us the area of this parallelogram, and we're after the area of the triangle, what have we got to do? Divide by 2. Because otherwise I'm going to get 2 triangles, right? Does that make sense? So, there's one way to look at it. Did anybody do something different than cutting 2 pieces out, put them together in a parallelogram? Yes.
I cut the triangle up and I got a rectangle.
You went clear back to Mama. Okay. Can you rearrange it back into the original triangle
Yes.
somehow?
Yes. Let's see here. Trying to remember. What does the original? Oh, I think we're going somewhere else.
So that's there.
She got it into a rectangle, now she's having trouble getting it back to the original triangle.
I would have been able to do it last night, but
There you go. That's why you have one backwards from the others.
Okay.
Bless you.
Let me, oops, see if I can. So, that was,
You have a big one on bottom, the medium one is backwards,
Yeah.
and then, yeah, the thin one is.
okay, so here's the one you were given, right? By the way, what is the height of that triangle?
5.
5, right?
5 or 6, depending on which one you're considering the base.
Oh, yeah.
What's the base?
If the base is the one that is
that one?
On the line.
3 long, is that right? Yeah. If the base is the 3 long, then the height is 1, 2, 3, 4, 5, right? Everybody agree with this? Well, Aubrey cut it at, if you'll count with me here, up 1, 2 and a half. So she took, well, let's just draw it here. Let's take this same one again. She cut it exactly halfway up. If this was 5, she cut it up 2 and a half. Okay? Then she cut this down like that. And there it is. Took the pieces. Now let's see if I can put them together again. You do it. And then, let's see here.
Oh, yeah.
Small.
Yeah, no, but I want it back into the rectangle.
Oh.
Oh,
Should do that. I don't remember how you had the. I assume.
There we go.
Hey, it's big, medium, so or it's big, small, medium.
So she took this piece right here, put it right there, and then took this piece over and put it right there. So this piece got to there, and that one to there. You with me?
I did it and I'm not with you.
Okay. This piece here got just slid over, and this one got tipped
Yeah, yeah.
around.
Mhm.
And now I've got a,
There it is.
okay, I've got a rectangle. What's the area of a rectangle? L times W. Well, what's our L? What is it? It's the original base of the, okay, what's our W? Half the original height. It's half the height, it's half of this. So it's 1/2 h. So using Mama's formula, length times width, we're going to get 1/2 h times b. There's our width times our length, or our length times our width. Are those two the same? Algebraically? Okay. Did anybody do it a different way? There are other ways, you know. Are we working hard at this? Everybody got at least one way though, right? Was this one the most common one? Okay. All right, we got us a formula now. It's just like a parallelogram, but we're going to cut it in half, right? Every triangle you can duplicate and turn it into a parallelogram with the other piece. All right. You have a sheet. It's called Finding Areas. I'd like you to, either alone or with partners, whatever you feel comfortable doing, find the area of each of those objects. Here's what we want to do. We want to say that if I enclose 4 like this, that's 1, those are centimeters, 1 centimeter squared. So each little square is 1 centimeter square. Okay? So I need you to give me the areas of each of those 10 objects in square centimeters. Do whatever you need to do, including using your geoboard if it helps.